The next sum is chosen from Irodov, sum number 3.22. Irodov, sum number 3.22. It's also a case of Maxima-minima, and that also comes from electrostatics. Okay, we see what is that. See, if you have thin, infinitely long, uniform line of charge, thin, infinitely long, uniform line of charge having linear density lambda, then at any point P, say at a distance x, let's say uniformly charged, point P is at a distance x from the line of charge, then electric field E is lambda by 2 pi epsilon naught x. This you should remember. So imagine this infinitely long, then at all points surrounding this at a distance x, the magnitude of the electric field will be lambda by 2 pi epsilon naught x. The distances of the points are same, then electric field magnitude would be same. Understand that? The question here is, you have two such long threads. You can take them to be infinite line of charge. Okay? Two such infinitely long line of charge separated by a distance, say L. Okay, they are separated by a distance L. You are supposed to find in a symmetry plane. In a symmetry plane, that means it is equidistant from these two and it is perpendicular to the plane containing the two lines of charge. The plane is equidistant from the two threads, and also it is perpendicular to the plane containing the two lines of charge. Such a plane we can take to be symmetry plane. In such a symmetry plane, what is the maximum value of the electric field intensity? What is the maximum value of electric field intensity? Now we change the diagram a little. Let's say the lines of charge go into the plane. One line of charge, another line of charge. Let's say they are separated by a distance L, and symmetry plane is shown like this, equidistant from the two. Charges go like this. This is the symmetry plane. Now on the symmetry plane, at what is the maximum electric field possible? Lot of different methods are there to do this sum. We can see how easily we can solve this. How easily we can solve the sum. Say you take a point P somewhere here, and the electric field at this point due to this will be away from this, say E. Electric field at this point due to this again will be away from this, say E. Magnitude of the electric field same because the distance is same. It's a symmetry plane, remember that. Symmetry plane. Symmetry plane. So join this like this. You say this is the point P. Just consider this angle as theta, so will this angle also be. Then if this is theta, this will be 90 minus theta. This also will be 90 minus theta. So this is one line, this is the line vertically opposite angle. This also will be 90 minus theta. This also will be 90 minus theta. Now you resolve this electric field into two components, and so you also resolve this into two components. The components parallel to this will cancel out. See here, this side the component will be E into, here you will have, this side it will be sine, so it will be cos of this, or sine of 90 minus theta, so cos theta. The component here will be component of the electric field in this direction, a line along the direction, along this direction. Similarly, the electric field which you resolve this way, it will be E cos theta, point P. The two electric fields will cancel, equal in magnitude, opposite in direction. Then the other two components will get added up. See, along this direction, maybe a little longer, maybe a little longer. E sin theta of due to this plus E sin theta due to this. So 2 E sin theta, where theta is this. You take this distance as say y. Therefore, the effective electric field, please note that these two will get cancelled. So the effective electric field, say E naught is equal to 2E sin theta, 2E sin theta, 2 into E lambda by 2 pi epsilon naught x sin theta. It's better if you do the sum in terms of theta. So keep theta as it is, change this x and say whether you can get it in terms of theta. Come to this. Say cos theta for x, you put this. E naught will be 2 lambda by 2 pi epsilon naught, x is L by 2 cos theta, already one sin theta is there, so you get this. So what do you have now? E naught is the electric field at this point. If you want, you can cancel out this 2 and 2. Lambda by pi epsilon naught L, 2 sin theta cos theta sin 2 theta. Okay, this is sin 2 theta multiplied by L, lambda by pi epsilon naught, lambda by pi epsilon naught L. Now you want to find the maximum value of the electric field. Simply take sin 2 theta as 1. Therefore, maximum value of the electric field E naught is equal to, or E max, on the symmetry plane will be lambda by pi epsilon naught L. Easy. Midway between these two infinitely long line of charges, electric field is 0. Somewhere at a very large distance also it has to be 0. Therefore, you have a chance that somewhere in between it will be maximum. That maximum value of the electric field, lambda by pi epsilon naught L. Is it clear? Yeah. Now, if you want to plot a graph between electric field versus this distance. So I want this now for plotting the graph's sake, let's say that you express the expression for the electric field in terms of, say, some distance y. So what I have to do, I'll change this sin theta and this x, everything to be in terms of y. See how to do that. See here, E naught is equal to 2 lambda by 2 pi epsilon naught. Sin theta will be y by x. Already one x is there, so y by x square. 2 into lambda by 2 pi epsilon naught, y by x square is y square plus L squared by 4. This is L by 2, square it. Therefore, you get the expression for the electric field intensity. Okay, maybe this 2 will go. Lambda by pi epsilon naught 4y by 4y square plus L square. This is electric field at a distance y from the center. You can differentiate it, equate it to 0, then also you will get the maximum value of the electric field, but that method is much quicker. So if you draw a graph between electric field and this y, if you want to draw a graph, and you see the graph should be like this. Maybe I'll rub this off. Okay. According to this. So you'll get somewhat like this. Okay. Electric field, distance y. What is the maximum value of the electric field? Lambda by epsilon naught L. Lambda by pi epsilon naught L. Pi epsilon naught L. That's electric field. Similarly, this will be minus. You see, these are the maxima here, this is the minima here. Absolute maximum, global minimum, because the curve runs parallel to the y-axis. Now if you see here somewhere, these 2 points, somewhere we have to do calculations if you want to locate the point, but otherwise, you see here, from here to here you can take, the curve is concave down, then it changes its nature, it concave up. So concave down to concave up, it changes at this point. So this is an inflection point, point of inflection. Similarly here also, concave down, concave up, this is another point of inflection. If you want to calculate the point of inflection, it is possible. Some other day we see whether we will take up the topic how to calculate or how to locate the point of or points of inflection. Understood that? So this is how we will have to do that maxima minima cases. When theta is 45, 2 theta is 90, electric field will be maximum, or theta is 45, you will get the electric field maximum. Understood that? Thank you.